Dear students, myself Bonifus PL. This is the last session of your second module of ECT201 solid state devices. So in this session we will be seeing the concepts of diffusion and recombination, and we will be deriving continuity equation. Then we will see diffusion equations. Then we will see the concept of steady state carrier injection. Then we will derive diffusion length equations. And finally we will see gradients in Quasi-Fermi levels. Effects of recombination on diffusion of excess carriers have been neglected till. If you consider the previous sessions, we haven't considered the recombination part. So this part we will be considering the recombination of excess carriers. So here the effects of recombination should be considered, as recombination can cause a variation in the carrier distribution. As an example, you can see this diagram here. Let delta x be a differential length with area A in a semiconductor sample in YZ plane. The whole current density leaving the volume, that is Jp of x plus delta x, can be larger or smaller than carrier density entering this particular volume, which is Jp of x, depending on the generation and recombination taking place inside this semiconductor piece or semiconductor sample. Means your Jp of x plus delta x can be larger or smaller than Jp of x, depending on what is taken inside this differential length. Here, net increase in hole concentration per unit time, that is dou P by dou T, inside this particular selected volume, is the difference between hole flux per unit volume entering and leaving minus the recombination rate. So in the last session, you have seen the equation for current density, which is current per unit area. So to convert current density to whole particle flux density, we need to divide current density by Q. Here we are considering whole, so we need to divide the whole current density by charge plus Q. Then dividing that flux density, that is Jp of x by Q by delta x, gives number of carriers per unit volume entering delta x into A per unit time. That means, in the previous diagram, number of carriers entering this volume. Similarly, if you take the leaving current density, that is Jp of x plus delta x, then divide it with Q, you will get whole particle flux density leaving that particular volume. Then if you divide that particular quantity by delta x, you will get number of holes leaving per unit volume at that time. So mathematically we can write it like net increase in hole concentration per unit time, that is dou P by dou T, when our holes are moving from x to x plus delta x, is given by change in carrier concentration. This first step. Change in carrier concentration, which is number of electrons, number of holes entering minus number of holes leaving at that particular volume minus recombination rate. Once again, rate of hole buildup is equal to increase of hole concentration in delta x A per unit time minus recombination rate. Now, we will be assuming delta x will be tending to 0. So, once delta x is tending to 0, you can see this first part of the equation. That is this one. So, this part when delta x tending to 0. So, that is equal to derivative minus derivative of jp of x, or from the basic concepts of the derivation, we can write limit delta x tends to 0, jp of x plus delta x minus jp of x divided by delta x will be equal to derivative of jp with respect to x. Here it is jp of x minus jp of x plus delta x by delta x. So when delta x tends to 0, this will be becoming minus derivative of jp by x. So once again, so when delta x tends to 0, this first part of our equation will become minus derivative of jp with respect to x. So as delta x tends to 0, our previous equation, which can be modified like this one, that is dou p by dou t will be equal to minus 1 by q dou jp e divided by dou x minus delta p by dou p. So which is called continuity equation for holes. Similarly, we can write continuity equation for electrons as dou delta n by dou t equal to 1 by q dou jn by dou x minus delta n by dou n. So remember or note that sign of the 1 by q term. For holes, the sign is minus, and for electrons, the sign is plus. So when the current is carried strictly by diffusion, in the previous session you have seen diffusion current equation as for electrons, which is q into dn, derivative of n with respect to x. So here, when as we are considering excess carriers, jn of diffusion is equal to q into dn dou by dou x of delta n. Now we will be substituting this particular diffusion current equation, that is equation number 32, into equation number 31b, that is the continuity equation for electrons. That is, we will be substituting this jn to here. Then we will get the expression as dou by dou t of delta n equal to dn dou square delta n by dou x square minus delta n dou n. Similarly, and this one is called diffusion equation for electrons. Similarly, for holes, you can derive diffusion equation as dou by dou t of delta p equal to dp into dou square delta p by dou x square minus delta p by dou n. So the next part we are going to see steady state carrier injection, and we will be seeing the equation for diffusion length. So as we discussed in the previous sessions, steady state condition means the properties of the system do not vary with respect to time. So in these two equations for diffusion of electrons and holes, the time derivative part should be equal to 0 for steady state condition. That means the properties of the system should not change with respect to time. So if in these two equations, that is equation number 33a and in 33b, the time derivative is 0, we'll get this as a second order equation, second order differential equation. See? So in the previous equations, this time derivative part is 0. So the remaining part, which is equal to 0, or we can write in the from equation number 33a, dn dou square delta n by dou x square equal to delta n by tau n. So that is what it is written over here. The difference is that instead of tau, we are having d. The reason is that in the previous case, we have considered both x and t. But now, for steady state carrier injection, our time derivative is to be 0. So we can take it as full derivative. So similarly, we can write equation for holes also. First one is equation for electron and second one is equation for holes. Now, approximating this equation as tau delta n by ln square, and in the second equation for holes just delta p by lp square. So ln square will be equal to dn tau n and lp square will be equal to dp tau p, or we can write ln equal to root of tau n and dn tau n and lp equal to root of dp into tau p, where ln and lp are electron diffusion length and hole diffusion length respectively. And comparing to the previous equation, partial derivatives are no longer required since the time variation is 0 for steady state. So now we will see the steady state carrier injection in detail. Okay, consider this plot. Here in x-axis we are having distance 0 to x, and in the y-axis we are having hole concentration, instantaneous hole concentration. So initially at thermal equilibrium that value will be 0, P0, that value will be P0. Now to understand the significance of diffusion length, assume excess holes are somehow injected into a semi-infinite semiconductor bar at x equal to 0, and steady state hole injection maintains a constant excess hole concentration at injection point, which is capital delta P. We are somehow injecting excess holes at x equal to 0 point. So equilibrium holes was P0. In addition to that, we are creating some excess holes which is equal to capital delta P. Now, as time increases, these excess holes generated will diffuse across the semiconductor bar, recombining with a characteristic lifetime tau p. So after tau p time, these excess carriers will be fully recombined. You won't be having any excess carriers. So to tell about the instantaneous value of the excess carriers, we will use the term small delta p of x. and for the excess carriers initial value we will use the term capital delta P. And now we will be doing some mathematical derivations, and we will be finding that total hole concentration or total instantaneous hole concentration P of x, which will be equal to P0, that is equilibrium hole concentration, plus instantaneous value of excess hole concentration, which is small delta P of x. And we will be proving that this small delta P of x will be equal to capital delta P into e to the power minus x by Lp. Then we will prove that the current density due to this instantaneous hole concentration P of x, that is Jp of x, will be equal to minus q into dp d by dx of P of x, which is equal to q into dp by Lp small delta P of x. So now what we are going to do is that we'll take the previous diffusion equation for holes, that is this equation 434b, d square delta P by dx square equal to tau P by Lp square. So we will be rearranging this equation. So once we rearrange this equation, we can write it as d square tau P by dx square, that is second order term. We don't have any first order term, so we can write it as plus 0 into d by dx of delta P, then that constant part, which is minus delta P by Lp square equal to 0. So if you solve this second order differential equation, we will get the solution for delta P of x, that is for excess holes. So the solution will be small delta P of x is equal to C1 e to the power x by Lp plus C2 e to the power minus x by Lp, where C1 and C2 are constants. Now we can calculate this C1 and C2 by applying boundary conditions. So we will be applying two boundary conditions. First one is, we will be assuming the case of x equal to infinity, and we will be considering the case of x equal to 0. Now if you see this previous plot, at x equal to infinity, that means at x equal to infinity, you don't have any excess carriers. We will be having only equilibrium holes, because all the excess carriers might have diffused. So the excess carrier concentration at x equal to infinity will be 0. Then x equal to 0. X equal to 0, we are having maximum number of excess holes, that is the initial value, which is capital delta P. So we will be applying these two conditions. So once we apply these two conditions, we will get C1 as 0 and C2 as capital delta P. And the solution will become, here C1 is 0, so this term will go 0, and C2 we will get it as capital delta P. So we will get small delta P of x equal to capital delta P into e to the power minus x by Lp. So the meaning is that injected excess hole concentration die out exponentially in x due to recombination. That means at x equal to 0, if x is equal to 0, we will get small delta P of 0 will be equal to capital delta P, because it will be e to the power 0. Now, as x increases, we will be having some negative exponential. So as negative exponential grow, our excess carrier concentration will decay exponentially, and Lp is the average distance a hole diffuses before its recombination. Now we will be assuming that a hole injected at x equal to 0 will survive till the point x. Then it will recombine in a further interval dx. So we need to find the probability of a hole that will survive till point x. Then we need to find the probability that it will recombine at the point in a further interval dx from x. So to find the probability of holes that will survive till x can be found by small delta p of x divided by holes injected at x equal to 0, that is capital delta p. So this small delta p of x by capital delta p will be equal to e to the power minus x by lp. This probability that a hole injected at x equal to 0 survives to x without any recombination is small delta p of x by capital delta p, which is equal to minus ex by lp from the previous equation. Now we need to find the probability that a hole at x will recombine in the subsequent interval dx. For that, we will be using the equation. First, consider the LHS part, that is holes at point x minus holes at point x plus dx, that is in the subsequent interval dx, divided by holes at initial point, and that is x. So we need to find the probability of holes that have recombined in the interval dx after x. So holes at point x minus holes at point x plus dx by holes at point x. Now we will be assuming dx is delta x is tending to dx and this dx is tending to 0. Then again by applying the basics of differential equation, we can write it as minus d by dx of delta p of x of dx by delta px. Once applying this delta x is tending to 0, your equation will become this one. Now we have expression for delta p of x. So delta p of x, we have capital delta p into e to the power minus x by lx, minus x by lp. That you need to substitute it over here, and you need to take the derivative. So once you, and here also you need to substitute for small delta p of x, which is capital delta p into e to the power minus x by lp. So after doing that mathematical steps, we will get the expression as 1 by lp into dx. So we have assumed the holes injected at point 0 survives till point x, and that probability is e to the power minus x by lp. Then in a further interval, these holes will recombine in that interval dx. So that probability is 1 by lp into dx. So the total probability that a hole injected at x equal to 0 will recombine in a given dx is the product of these two probabilities, that is e to the power minus x by lp into 1 by lp dx. So you can write that is just 1 by lp into e to the power minus x by lp dx. Now we need to find average distance a hole diffuses before recombining. So to find average, we can use the mathematical function. Suppose if you need to find the average of a function f of x, we can find average of f of x by taking integral of f of x from minus infinity to infinity f of x into probability of that function and dx. That is average of f of x, we can write it as integral minus infinity to infinity f of x p of x dx, where P of x is the probability of the function. So here we need to find the average distance x which a hole will travel before its recombination. So our function is x and our probability is this one, 1 by LP into e to the power minus x by LP. So we can write average distance a hole diffuses before its recombination. So to indicate the average, we use the symbol this one. Okay, average of x is equal to, and here we are considering only whole movement in one direction. If you just refer to the previous plot, we have started from 0 to x equal to infinity. So it's from 0 to infinity, that function x into probability of the function, that is e raised to minus x by LP divided by LP dx. And once we take integral of this function, we will get as LP. So steady state distribution of excess holes causes diffusion and therefore a hole current in the direction of decreasing concentration. Means from the previous plot, here diffusion is from left to right holes. So steady state diffusion of these excess holes will create a hole current in the same direction. Here hole current will be also in the direction from left to right. Now take the equations from the previous session, that is equation number 22b and 36 in your textbook. So those equations are, equation number 22b is the diffusion equation for holes, that is Jp of diffusion, which is equal to minus q into dp into dp by dx. And equation number 36, which is the excess carrier equation, that is small delta p of x equal to capital delta p into e to the power minus x by LP. So taking the first equation 22b, that is the diffusion equation, you can write diffusion equation is this one, first one, Jp of x, that is your Jp of x equal to minus q into dp d by dx of pa. So which is your diffusion equation, to which you need to apply equation number 36, that is x carrier equation, that is small delta p of x equal to capital delta p into e to the power minus x by LP. Now in the second term of this equation, diffusion equation, p, we have the term p. So p will be equal to equilibrium concentration. We have seen in that plot, P0 plus instantaneous excess carrier concentration, that is small delta P of x. Okay. So if you substitute this one, P equal to P0 plus small delta P of x over here, P0, that is equilibrium value, it's a constant value. So derivative of a constant is 0. So you will be having the remaining term minus q into dp d by dx of delta p of x. Now for this delta p of x, we have the equation capital delta p into e to the power minus x by LP, that you will be substituting. So you will get this expression. And once you take the derivative, you will get this one. And this term, small capital delta p into e to the power minus x by LP, which is nothing but small delta p of x. So finally, we will get the expression as q into dp by LP, small delta p of x. So once again I am repeating. We have diffusion current equation Jp of x equal to minus q into dp into d by dx of p. So into that p whole concentration we can substitute p0 plus small delta p of x. As p0 is constant, our equation will become minus q into dp into d by dx of delta p of x. This one. And to this delta p we need to substitute the equation. This one. Capital delta p into e to the power minus x by lp. That is equation number 36. So if you take the derivative, we'll get the expression as q into dp by lp, capital delta p into e to the power minus x by lp. And we know capital delta p into e to the power minus x by lp is instantaneous value of x concentration, that is small delta p of x. Next, we are going to see the concept of Quasi-Fermi levels. So we'll see gradients in the Quasi-Fermi levels. Earlier we have seen Fermi level. So those Fermi levels, it was for semiconductors at equilibrium. So at equilibrium, we are having a constant Fermi level. We don't have any gradients over that. Now, if there is any sort of current, that is drift or diffusion current, or any drift component or diffusion component, we are having net current, and there will be a gradient in the steady state Quasi-Fermi level. Then we won't be calling just the equilibrium Fermi level, we will be saying just Quasi-Fermi level. That means our Fermi levels will be varying, changing, and it will be having gradients. So from the previous session, our total electron current, which is the sum of drift and diffusion component, we can write it as Jn of x equal to q into mu n of x d of x plus q dn d by dx of n of x. So drift plus diffusion component. So in which the gradient in electron concentration, that is d by dx of n of x 10, that we will be taking. We will be taking the gradient of electron concentration d by dx of n of x. So what's the expression for n0? For n0, our expression was ni into e to the power ef minus ei divided by k into t. Here we are having drift and diffusion component. Because of that, we are having gradient in steady state Quasi-Fermi level. It is not equilibrium state. So we can't use the EF term. So instead of EF, we will be using Fn. So n of x, you can write it as ni into e to the power Fn minus ei divided by k into t. It is similar to the equation for n0, which was ni into e to the power ef minus ei divided by k into t. Instead of ef, we have kept it as Fn because it's a steady state value. Just keep on changing. Now, you take the derivative of this term, you'll get the expression as this one, n of x by k into t into d by dx of f of n minus d by dx of ei. Now, substitute it on the previous equation. 48, substitute it. So once you substitute, we will be having q dn n of x by k into t. Then we need to apply Einstein's law. Einstein's law, just last session you have seen, which is d by mu equal to kt by q. So once you apply that, after applying 49 to 48 and applying Einstein's law, we will get the expression as Jn of x equal to q mu n n of x ex plus mu n n of x into d by dx of f of n minus d by dx of ei. Now we will be using another equation. Electric field. electric field which is minus derivative of potential, that is minus d by dx of V of x. Then potential and energy relation. Potential and energy are related by potential divided by charge. So electric field divided by, once again, electric field and potential are related by electric field equal to minus d by dx of Vx, where Vx is potential. Then potential and energy level are related by V of x equal to E by minus Q. We are considering a particular energy level EI. So we will get the equation as 1 by Q d by dx of EI. Now we will be substituting this one to here. The first term of our equation 15. So once you apply that, the d by dx of EI term, that will cancel, and we will get the final expression as Jn of x equal to mu n n of x d by dx of Fn. So thus process of electron drift and diffusion are summed up by spatial variation of Quasi-Fermi level, because earlier we had two terms, drift and diffusion component for our electron current density. So we have converted that into a single term which consists of spatial variation of our Quasi-Fermi levels, or gradient of our Quasi-Fermi level. Now we will be modifying this equation slightly in the form of modified Ohm's law. So what we will be doing is that in the previous term, here we will divide by Fn by Q, and here we will multiply with Q. So dividing and multiply with Q, that won't change the value. So our equation will become Q mu n n of x d by dx of Fn by Q. Then Q mu n n of x, that is nothing but conductivity, sigma n of x. Similarly, for holes, we can write Jp of x equal to Q mu pp of x d by dx of Fp by Q equal to sigma p of x into d by dx of Fp by Q. So the equation 452a, which is for electron current density, and the equation 452b, which is for hole current density. If you go back to the previous equations, we have both drift and diffusion component. Now we have summed up those drift and diffusion component to a single term which is called gradient of Fermi level, Quasi-Fermi level. So if there is any drift, diffusion or its combination, the resulting current will be proportional to gradients of two Quasi-Fermi levels. Because in our device, the total current I will be equal to In of x plus Ip of x. Conversely, if there is a lack of current, that means we are having a constant Quasi-Fermi level. That means if you are having equilibrium state, there is no current flow. That means we don't have any gradients in this gradients over here. For the equilibrium value, Jn of x and Jp of x is 0. That means gradient of Fn and Fp are 0. We'll see other names of this Quasi-Fermi level. The first name is IMREF. Nothing but Fermi, we are writing it back, IMREF. And the second name is called electrochemical potential. So the reason for that name, we'll see. For current density, we have both drift and diffusion term for both electron and hole. Now, driving force for carriers is governed partly by electrical potential, which is called drift time, and other part is done by gradients of carrier concentration. So that gradients of carrier concentration will be treated as chemical potential, and drift part is carried as electrical potential. So combine those two, will be calling it as electrochemical potential. So with this we are winding up second module, and in this last session we have seen the diffusion and recombination concept. Then we have derived continuity equation. Then we have derived diffusion equation for both electrons and holes. Then we have seen the concept of steady state carrier injection, in which we have seen the equation for diffusion length. And finally we have seen gradients in Quasi-Fermi levels and how to modify our current equation, which consists of both drift and diffusion with gradient in Quasi-Fermi level. So thank you.